Gravity bends, yet on the largest scales, it doesn't behave as expected. Nearby, Newton and Einstein predict motion accurately, but far away, galaxies misbehave. Picture an apple falling, then zoom out to billions of galaxies. Gravity, in plain words, is the attraction between masses. This matters because galaxy motions reveal the universe's hidden content. Astronomers see stars orbiting faster than visible mass predicts. That discrepancy forces two options: unseen mass or changed gravity. Net result, gravity keeps secrets at cosmic distances. A spiral galaxy fills the frame, its arms glowing faintly. At its simplest, gravity is a pull between masses. This matters because orbital speeds depend on how that pull weakens. The inverse square rule says force falls with distance squared. Double the distance, and the force becomes 1/4. That rule predicts planetary motion and satellite orbits precisely. Yet observations show outer stars orbiting faster than expected. So the basic inverse square expectation fails on galactic scales. Think of space around a galaxy as a curved, stretching sheet. Einstein taught us gravity is geometry, mass curves spacetime. That matters because light and matter follow that curvature directly. Mass tells space how to bend, and space guides motion. Einstein's equations predict effects like gravitational lensing and time delays. Lensing bends background light, letting us map mass without motions. For example, clusters bend light into visible arcs around them. So geometry-based gravity gives extra, independent tests of mass distribution. Now picture a vast scaffold, filaments connecting galaxy clusters across emptiness. The cosmic web grew from tiny ripples after the Big Bang. This matters because gravity amplifies those ripples into the web we see. Gravity pulls matter into nodes and along long, thread-like filaments. Expansion stretches the gaps while gravity concentrates the knots. Simulations with dark matter reproduce the web's filamentary pattern well. For example, filaments can span tens of megaparsecs traced by galaxies. So large-scale structure supports models that include significant unseen mass. Nearby detectors and distant telescopes together form our gravity lab. Precision mapping measures motions, lensing, and background radiation signatures. This matters because different probes test gravity in different ways. Rotation curves probe dynamics, while lensing measures integrated mass along sightlines. The cosmic microwave background records early fluctuations shaped by gravity. Gravitational waves reveal how spacetime carries energy across distances. Combining probes reduces ambiguity and points toward consistent models. One survey measured lensing across millions of galaxies, constraining mass precisely. So multi-probe observations give a cross-checked, robust picture of gravity. Picture a clear rotation curve plot, velocity against radius from center. Rotation curves define the puzzle with tidy, numerical clarity. This matters because they quantify the failure of Newtonian expectations. Observed curves stay flat, where Newton predicts a steep decline. Adding an unseen halo of mass reproduces these flat rotation curves. A typical spiral needs about 5 to 10 times more dark mass. Visible stars account for only about 10 to 20% of mass, so rotation curves point strongly toward an unseen mass component. On the largest scales, cosmic expansion competes with gravity's pull. The universe expands, and gravity tries to slow that expansion locally. This matters because their balance shapes how structure forms over time. Dark energy accelerates expansion, changing gravity's effective influence across epochs. Some theories let gravity weaken at huge distances, mimicking dark energy. Observations of galaxy clustering track how growth rates evolved with redshift. Surveys measure growth to percent-level precision, testing these competing ideas. So expansion versus gravity sets the stage for cosmic history. Researchers test alternative gravity ideas with both experiments and observations. MOND changes force behavior at extremely low accelerations, reproducing many galaxies. That matters because MOND can fit rotation curves without dark matter. However, MOND struggles to explain clusters and the cosmic microwave background. Scalar tensor theories add fields that modify gravity under certain conditions. Those can hide deviations locally, yet reveal them on cosmic scales. A striking test used colliding clusters, separating lensing from baryonic gas. That observation favored particle dark matter by locating mass with galaxies. So tests narrow possibilities, but no definitive answer has emerged yet. Looking ahead, new telescopes will sharpen gravity's portrait dramatically. Euclid and Rubin will map billions of galaxies in exquisite detail. This matters because massive data will reveal subtle departures from standard gravity. They will combine redshifts, shapes, and lensing to constrain models tightly. Gravitational wave detectors add complementary constraints on gravity's propagation. Laboratory searches for dark matter particles pursue a direct particle explanation. Forecasts predict percent-level constraints on key cosmological parameters soon. So near-future data should settle many current ambiguities about gravity. We saw how stars orbit oddly, how light bends, and how structure forms. If you enjoyed this, follow for more curious cosmic explanations.